Hey there, everyone. Ready to do a deep dive with me into some number theory today?
Always up for a good deep dive.
Awesome. So today we're looking at a sequence in the OEIS. It's A00000049. And, well, it looks pretty simple at first, but...
Oh, yeah. These sequences can be deceptive.
Right. Totally. Like, it hides some really cool patterns.
Yeah.
We've got some excerpts from the OEIS entry itself.
Right.
And some notes, too, just to help us kind of break things down a bit.
Nice.
So you ready to jump in?
Absolutely. Let's do it.
Okay, so A00000049. The formal definition says it's the number of positive integers less than or equal to 2 to the power of n of the form 3 times x squared plus 4 times y squared.
Wow. That's
I know, right?
quite a mouthful.
It's a lot. I mean, I get the less than or equal to part, but
Yeah.
the rest of it's kind of,
It's a bit dense.
yeah,
Yeah.
making my head spin just a little.
Let's break it down then.
Yeah.
So imagine you have a recipe for making numbers.
Okay, I like where this is going.
All right. And this recipe, it uses two whole numbers. We can call them x and y.
Okay.
And the recipe involves squaring those numbers, multiplying them
right.
by 3 and 4, respectively,
Okay.
and then adding them together. So that's where we get our 3x plus 4y.
Okay, so like a mathematical baking show, basically.
Exactly.
We're trying to see what numbers we can bake
Yeah.
with this recipe. But there's a catch.
There is a catch. The n in our definition is like our oven size. It tells us the biggest number that we can bake.
Oh, okay.
And specifically, that size is 2 raised to the power of n.
So if n is 4,
Yeah,
our oven can only fit numbers up to 16.
exactly. Because 2 to the power of 4 is 16.
Right.
So we're looking at all the numbers that we can bake using our recipe that are less than or equal to 16.
Gotcha.
Does that make sense?
Yeah, that makes a lot more sense.
Okay, good.
So the OEIS entry gives us an example
Yeah.
for when n is 4, so they call that a 4.
Right.
So let's try it.
Let's walk through it.
If x is 1 and y is 0,
Okay.
our recipe, 3x plus 4yy, gives us 3.
Yep.
Which makes sense. 3 is less than 16.
It is.
What if we flip it around? If x is 0 and y is 1.
Okay, then we get 4, and we can keep going, right?
Right.
We tried different combinations of x and y,
Okay.
as long as the result is less than or equal to 16.
Okay, got it.
Yeah.
So if both x and y are 1, we get 7.
Yep.
What else? Oh, if x is 2 and y is 0, we get 12.
You got it.
And if x is 0 and y is 2, it's 16.
Perfect.
So that's 5 numbers in total.
Exactly. 5 numbers.
So that means A for the fourth term in the sequence is 5.
You got it.
Wait, only 5 numbers?
Yeah.
I feel like I was expecting a much longer list.
I know. It seems a little underwhelming at first.
Yeah. What makes it so special then?
Well, that's where it gets interesting, right? It's not just about listing numbers.
Okay.
It's about what those numbers tell us about our recipe.
Mm.
And mathematicians, they call this recipe a quadratic form.
Ooh, fancy. So our 3x plus 4y is an example of a quadratic form. What's so special about them?
Well, quadratic forms are kind of like building blocks in number theory. They help us understand how numbers relate to each other and which numbers can be built in specific ways.
So by studying A000049, we're actually learning something about these quadratic forms.
Exactly. This sequence, it's like a window into the behavior of this particular quadratic form. It tells us how many integers we can create using this specific recipe within a given range.
Okay. I think I'm starting to see why this is more than just a list of numbers now.
Good, good.
It's like we're using this sequence to explore these deeper mathematical concepts.
Exactly. And what's cool is that each term in the sequence, it summarizes a whole bunch of calculations behind the scenes.
Really?
Yeah. Each number represents all the possible x, y pairs
Right.
that work for that particular n.
So each term is like a snapshot of all the successful number baking attempts
Exactly.
for a given oven size.
You got it.
That's a neat way to think about it.
Isn't it? What's also fascinating is that not all numbers can be baked this way.
Really?
Yeah, that's part of what makes A000049 interesting. It highlights the limitations of this specific quadratic form.
So some numbers are just off the menu, huh?
I guess you could say that.
I'm starting to see why number theorists get so excited about this. It's like a mathematical detective story, right?
Yeah,
Trying to figure out which numbers work and why.
exactly. And that's what makes these quadratic forms so fascinating, right? They create this sort of numerical sieve,
Oh, we just
allowing some numbers to pass through while others get blocked.
a numerical sieve. I like that.
Yeah.
So are there like other sequences in the OEIS that use different quadratic forms? different sieves.
Oh, absolutely. Yeah. The OEIS is chock full of sequences based on different quadratic forms, each with its own little unique set of allowed numbers.
So, like, each one's sifting for something a little different.
Yeah, exactly.
Yeah.
Actually, this entry mentions another sequence, A020677.
Yeah, I see that in the cross-refs section.
Yeah.
What's the connection there?
So that sequence, it deals with the sums of squares instead of a specific combination like R3x Sandoval plus 4y minute.
Okay.
So it kind of highlights how our sequence fits into this wider family of problems that are all about representing numbers using squares.
So by studying all these like square-based sequences,
Yeah.
mathematicians can start to see like the bigger picture
Exactly.
of how numbers can be built and categorized.
You got it. That's one of the things that makes number theory so exciting, right? And
Yeah.
you start with this seemingly simple question
Right.
about a specific sequence, but it leads you to these broader insights about the structure of numbers themselves.
It's like each sequence is a piece of a giant jigsaw puzzle.
Yeah, that's a great way to put it.
Right. And the more pieces we find,
Yeah,
the clearer that overall picture becomes.
absolutely.
But I have to admit, I'm still a little fuzzy on what makes certain quadratic forms like more interest to mathematicians than others. Is it just about like how many numbers they can generate?
That's a great question. No, it's not just about quantity. It's about the kinds of patterns and relationships that emerge.
Okay.
Some quadratic forms, they have these really special properties that connect them to other areas of math, like geometry or even cryptography.
Oh, wow. I had no idea number theory could like connect to things like cryptography.
Oh, yeah.
I always thought of it as a very like pure abstract
Right.
field.
It is abstract, but that doesn't mean it's isolated, right? Math is all about connections.
Mm-hmm.
And sometimes the most surprising insights come from linking seemingly unrelated concepts.
Okay. My mind is officially blown. So with A000049, what kind of patterns like are mathematicians looking for? Is it about how fast the sequence grows or maybe like special types of numbers that appear?
All of those things are important. Yeah. Number theorists might look for repeating patterns within the sequence, or they might analyze how the sequence grows as n gets larger.
So they might ask, like, does the number of integers we can bake
Yeah.
with our 3x Sansalum plus $4 recipe increase
Yeah.
in a predictable way as our oven size grows?
Exactly. They might also investigate whether certain types of numbers, like prime numbers, are more or less likely to appear in the sequence.
So it's like they're trying to decode like the hidden messages
Yeah.
within this sequence of numbers,
Mm-hmm.
searching for like clues about the deeper structure of the
Yeah.
mathematical universe.
That's a very poetic way to put it.
Uh-huh.
But you're not far off. I mean, number theory really is about finding order and meaning in this seemingly random world of numbers.
And sometimes those patterns like can lead to these groundbreaking discoveries that have like real world applications.
Absolutely. Just think about cryptography, right? The security of our online transactions relies on the properties of prime numbers,
Right.
which are a fundamental topic in number theory.
That's amazing. So something as abstract as studying like how many integers fit a certain quadratic form
Right.
could actually have like implications for the security
Yeah.
of our digital world.
It might sound far-fetched, but that's the beauty of math, right? The most unexpected connections can emerge, and pure theoretical research can sometimes lead to these practical breakthroughs.
Okay. I'm starting to see why people get so passionate about number theory. It's like a treasure hunt
Yeah.
where the treasure is knowledge itself.
Mhm.
But I have to be honest, like looking at this sequence as just a list of numbers, it's hard for me to like grasp those deeper connections. Is there a way to make these patterns more visual, more like intuitive?
That's a fantastic question, and it leads us to another powerful tool in number theory: visual representation.
So we've talked about this sequence A000049 as like a numerical sieve,
Right.
and how it relates to this specific quadratic form. But I'm still kind of stuck on like how abstract it all feels.
Mhm.
Is there a
Yeah.
way to like actually see what's going on with these numbers?
You're thinking along the right lines. Sometimes a visual representation can really help us grasp these complex mathematical concepts, make it a little more intuitive.
So like instead of just listing the numbers in the sequence,
Yeah.
could we like create some sort of image or graph that that represents them.
Exactly.
Maybe that would make the patterns a little more obvious.
Remember those XY pairs we were talking about?
Uh-huh.
The ones we plug into the quadratic form to bake our numbers?
Yeah.
We can actually think of those pairs as coordinates on a graph.
Oh, like a treasure map where
Yeah.
each XY pair leads to a specific number.
That's a great way to think about it.
That fits our recipe.
And by plotting all the XY pairs that generate numbers within our sequence, we might start to see some really interesting visual patterns emerge.
So if we imagine like a grid, each successful number baking attempt, so those pairs that give us a number less than or equal to 2 to the power of n, would light up a point on that grid.
Exactly. And then as n increases, as our oven size expands, more and more points would light up. And we could see how this constellation of numbers grows and evolves.
Wow, that's a really cool way to visualize it. It's like each term in the sequence is like a snapshot of this growing constellation.
Right.
At a different scale.
Yeah.
Do mathematicians actually use like visual representations like this?
Yeah.
When they're studying number theory?
Oh, they do, yeah. Visualizing data can often reveal these hidden patterns that might not be obvious from just, looking at a list of numbers.
Right.
And in some cases, these visual representations can even like inspire new mathematical discoveries.
It makes you realize that math isn't just about like equations and formulas.
Right.
It's also about like creativity and imagination.
Yep.
You have to be able to see the problem from like different angles.
Yeah.
To really understand it.
You got it. And that's what makes number theory so captivating. It's this field where beauty and logic intertwine, where abstract concepts can be brought to life through these visual representations.
Well, this deep dive has definitely been an eye-opener for me. We started with this seemingly simple sequence of integers, and we ended up exploring quadratic forms, numerical sieves, and even the idea that numbers can be visualized as like constellations on a graph. I'm starting to see the world of numbers in a whole new light.
That's great to hear. And that's what we hope to achieve with these deep dives, right? Spark your curiosity, challenge your assumptions, and maybe even inspire you to explore the hidden depths of the mathematical universe.
So for our listeners who are now like totally inspired to explore A000049 further, what would you suggest as a next step?
I would say fire up a graphing program or grab a piece of graph paper and start plotting those XYs.
Yeah.
See what kind of visual patterns you can create. You might even discover something new that mathematicians haven't noticed before.
That's a great challenge. And even if we don't make any groundbreaking discoveries, the act of exploring these patterns, I think, can be incredibly rewarding in itself. Thanks for joining us on this deep dive into the fascinating world of number theory. Until next time, keep those minds curious and those numbers crunching.